This is going to be a little different from other tau stats videos that we've created. A lot of those videos are a little bit shorter, a little bit sweeter. This one is going to be pretty in-depth. And what we're going to look at is the run Coinbase code inside the subtensor for Bittensor. If you've watched other videos on our YouTube channel, you've probably seen charts like this, which walk through how one alpha is distributed amongst the owners, the validators, and the miners, and then how all of that gets split up and down to the stakeholders. This is not that same video. In this video, we're going to go line by line through some Rust code. If you're not a Rust coder, that's fine. I am not a Rust coder either, but I've taught myself to read it. And so we'll walk through it and explain what each one of the lines is doing inside the code. But we're going to go pretty in depth and explore exactly how all of the tau and alpha is delivered every single block, and then every single epoch for every subnet. It doesn't actually look like the chart that I've been showing in all of those other YouTube videos. It looks a little bit more like this. And there's some very good reasons as to why it's not distributed the way that feels a little bit more logical, or at least it feels logical to me. It's distributed this way. And the main reason is this work needs to be done every single block. When that one alpha is distributed amongst all the stakeholders, we need to know the root alpha split, because the root proportion changes every single block. Now, it's not something that you or I would see. It's down in like the 5th or 6th decimal place, but it does change every single block. And then whatever alpha is going to be sold to root for the root stakeholders, that has to be done every single block. The price changes every single block. So this is done every block. And then at the end of the epoch, which for most subnets is 360 blocks, the rest of this all happens. With all of that, let's get started. So we're in the run Coinbase. We're going to start about line 35, and we're calling the run Coinbase. The first thing we need to do, step 0, is get the current block. So it calls the chain and says, hey, what's the latest block? And we get a block number. Okay. And now the next thing we want to do is we want to know all of the subnets, because this code that I'm showing it for just one subnet. Of course, it's running across every single subnet, every single block. So the first thing we do is we call the chain and we say, hey, give us all the net UIDs, all of the subnet numbers. And then, as you know, there's a whole lot of subnets. But we need to do a little more. We need to filter out the subnets that aren't active yet. So when a new subnet registers, they're not active. They don't get any emission. We don't want to calculate the run Coinbase for them. So we're going to filter them out. And so the way we do that is we look for they have to have a first emission block number. All active subnets have emission block numbers. And when you activate your inactive subnet, you get a first emission block number. Therefore, it will appear. Now we have a slightly smaller list without those inactive subnets. Now, when we run this, we can loop through all of the subnets we want to emit to. Now, what we need to do is we need to calculate the prices. And so the way emission works for tau is we need to know the sum of all of the subnet prices. So what we're going to do is for every single subnet in the subnets we're emitting to, we are going to add up the all of the prices. So we have total moving prices is 0. We loop through all the subnets that we can emit to, and then for total moving prices, we add the moving price for that subnet. And so that's going to give us, once we loop through all the subnets, we're going to have the total moving price, right? Which is what's reported at tau stats as the sum of subnet prices. Okay, so now we have the sum of the subnet prices. It's time for step 3. We're going to get the tau in, the tau that's emitted into the liquidity pool for the subnet, the alpha in, the alpha emitted into the liquidity pool, and the alpha out. That's the alpha that's emitted to all of the stakeholders and distributed to the owners, the miners, and the validators. We're going to spend a lot of time there, but let's just get through this first part. So tau in is defined as the price of that subnet divided by the sum of all of the prices, which is why we got the sum of the prices earlier. So for all of the subnets that we can emit to, let's get the subnet price from the chain, and then the moving price from the chain. And then tau in is block emission. And so block emission is defined as 1 right now. At the halving, it will be 0.5. At the second halving, it'll be 0.25, et cetera, et cetera. I don't show that here because we're still in the first halving and there's just a 1 out in front. We multiply it times the moving price, and then we divide it in a checked div. Make sure you're not dividing by 0 because that would be bad and it would crash the chain. So we divide it by the total moving prices, and that's going to give us our tau in. We're now ready to do our alpha in and our alpha out. Alpha emission is again 1. So we're going to pull out the emission of alpha, which is 1 right now. At the alpha halving, it'll go down to a half, et cetera, et cetera. So alpha in is defined as tau in divided by the alpha price. So we take tau in and do that checked division by the alpha price, just to make sure we're not dividing by 0. And that's going to give us our alpha in. This min here means that it's going to take the smallest number of alpha emission, which is 1, or this ratio here. What that means is the largest value that you can have for alpha in I, for the alpha in, is 1. And then alpha out is going to be 1 right now. And at the halving, it'll be 0.5, et cetera, et cetera. Okay, but the next step is we only put tau into the subnet pool if the network allows registration. If registrations are turned off, no tau is emitted to the subnet. So if registration is not allowed, or proof of work registration is not allowed, we set tau in to 0. So if on your subnet you've turned off registration, there's no tau for you. Now that we've collected those, we insert those into the map, the tau in, the alpha in, and the alpha out for that subnet. And now we've collected the emission. After we loop through all the subnets, we've collected all of the emission for tau, alpha in, those are going into the pool, and then alpha out, which is distributed to stakeholders in the subnet. Now that we've collected it, it's time to inject that into the pool. So this is actually going to change the pool liquidity at each block. So when you inject the alpha in, you increase, we take the alpha in emission, and then we just add the alpha in to the total. We do the same thing with alpha out. We grab the alpha out emission, and we add that into the total. And then, as you might imagine, we do the same thing with tau in. We take the tau in emission, we add our new tau into the total. There are a couple other places where we track the amount of tau. So we have to increase the total issuance, and then we increase the total amount staked of tau. And so this is just adding it into the sum of the total stake and the total issuance. This is again done for every single subnet. All right, so now we've injected tau and alpha into the liquidity pool. We've added our 1 alpha to be distributed amongst all of the participants. And now we're starting that distribution. The first thing we do is compute the owner cut. So the cut percent we can pull. It's saved as a pseudo variable, and we can pull that out at 18%. So for every subnet in the subnets we can loop through, we get the alpha out. It's 1 right now for everybody. And we calculate the owner cut. The owner cut is alpha out, again, 1 times 0.18. So we get that 0.18 here, and we save that. So we save that into the owner cuts. And then we have a new alpha out. So alpha out is now alpha out I minus the owner cut. So this is now 0.82. So that's everybody else. And then we accumulate that pending owner cut. Because remember, we're doing this every block, but we have to accumulate that into a pending variable that then when we run the epoch, we can distribute. So here we are. We've done that first step. We split that 1 alpha into 0.18 and to 0.82. We can also show it here as a chart, just ongoing as we go through the code. All right, so now we've got the 80.82 alpha out that goes to the miners and the validators, but we need to separate out the root dividends and sell them. And then we're going to accumulate those dividends for later, for when we're running the epoch. So again, we're going to loop through all of the subnets. We're going to get that remaining alpha out, and for all of them, it's going to be 0.82. And then we're going to find the total tau on root. And the reason for that is we need to calculate that root proportion. How much of the validator stake goes to root? How much of it stays to the alpha stakeholders? And the root proportion is the tau weight, which is set on chain at 0.18, the amount of tau staked to root, and then the total amount of alpha issued. So we're going to get the amount of tau on root. So we pull that out for the chain. We're going to get the total amount of alpha on the subnet. So the alpha issuance, we can pull that from the chain. That's this number here. We're going to get the tau weight. And in here, they're using tau weight two different ways. They're going to pull the tau weight, that 0.18 variable, and multiply it times the root tau to make this variable tau weight and this variable tau weight, because they're taking the constant tau weight and multiplying times the root tau and then calling it tau weight. So now root proportion is this variable of tau weight, which is actually these two terms combined, divided by, and then remember it's a safe division here, divided by this tau weight plus the total amount of alpha. And so that gives us our root proportion on this block for this subnet. Okay, now that we have the root proportion, the root alpha is going to be the root proportion times the alpha out, that 0.82. And then we're going to multiply it times 1/2, because 50% goes to validators and 50% goes to miners. And so our root alpha is 0.5 times 0.82 times 0.05, 0.205. So then we remove that alpha from the alpha out. So the pending alpha, we're going to rename this, is now alpha out minus this. So pending alpha is 0.82 minus 0.205, so 0.605. And so now what we've done is we've calculated the root alpha split. We have the amount of alpha going to root, and then we have the amount of alpha going to everybody else. It's called pending alpha. So we're at 18, 20.5, because I just decided for this video that root proportion is 50%, and then 60.5 in pending alpha. Now that we have that root alpha, we need to sell that every single block. So we're going to call the root tau. We're going to call this swap alpha for tau, and we're going to for this subnet and the amount of alpha that we're going to sell. So now we have to walk through this swap alpha for tau, which calls the sim swap alpha for tau. And the math that happens here, it's a liquidity pool. So the amount of alpha being unstaked is here. Here's the tau pool, the alpha pool, a K, and that's going to tell us how much tau is going to be received to be distributed amongst all of the validators and stakeholders en route. So now we're going to do that math. So there's two mechanisms for swapping alpha for tau. Mechanism 0 is on the root subnet, where it's tau to tau. It's different. Mechanism 1 is the d tau, where we're selling alpha to get tau. So the first thing we're going to do is we're going to find the amount of tau in the pool. We're going to find the amount of alpha in the pool. So subnet alpha in, we're going to pull that off of the chain. And then K, this constant is the product. It's alpha times tau. So the amount of alpha in the pool times the amount of tau in the pool. And that gives us K. They call this part of the formula the new tau reserve. So that's K divided by the alpha plus the amount of alpha that is being sold. And then the amount of tau that's being received is equal to the tau reserves, the amount of tau in the pool, minus subtracted, we subtract off the new tau reserves, this value, and that gives us the tau received. And then we're going to do a minimum here because it could also be 0 if there's no liquidity. Now that we've done that now that we've decided how much is going to be transferred, we need to adjust all of the liquidity pools. The amount of alpha out is going to decrease because we're taking alpha out and putting it into the alpha in, which increases alpha in. And then tau is coming out of the pool to be distributed to the stakeholders. So we have to reduce the amount of tau in the liquidity pool. And then the amount of tau being staked is also being decreased by that same amount. This is just sort of that global tracking of the tau over time. And then we also track the amount of tau being bought and sold inside each subnet. So that increases the volume of tau moving in and out of the liquidity pool. And then we return the amount of tau that we've calculated. So now that we've sold it, we've now completed everything that needs to be done inside that first block. So we're going to accumulate the pending alpha swapped, the pending emission, which is all of this over here. We're going to also accumulate the root, the tau that we calculated. And if you remember early on, we added the pending owner's cut earlier in the video. So now we're ready. We're at the end of that first block. But before we can end that first block, we need to change the price, because that little bit of alpha and that little bit of tau is going to change the price. And there also have been transactions possibly during that block. And so we need to update the moving price of the alpha in the subnet. And now we've completed that first block. So after one block, we've got a couple storage things. We've got the pending owner emission, the pending tau, and the pending root alpha, and then the pending everything else, alpha stake and minor stake. And now we're done with that first block worth of information, and we're ready to move on to, once the epoch has been completed, to run the epoch and distribute all of this to all of the stakeholders. We're now to step 7 of the run Coinbase, where we're going to drain the emission based on the tempo. And so what happens is we're going to run through for every subnet, and we're going to see, should we run the epoch? Have we hit that point where most subnets have 360 blocks in the epoch? If we've hit that limit, then we should run the epoch. So the first thing that happens if we're going to run the epoch is we're going to restart all the counters. The blocks since the last step. Since we last did it, we're going to set to 0. Right? We're going to set the current block where the mechanism run is the current block. And then we're going to get the pending emission, the pending root divs, the pending alpha swapped, and the pending owner cut, and pop those into variables and reset those to 0 for the next epoch. So you can see we take the pending alpha emission, put it in this variable, and then reset the pending placeholder to 0 for the next epoch. And then we need to drain all of those pending root divs, alpha emission, and owner cut. So we're going to run this drain pending emission. And that comes down to over here. So the first thing we're going to do is get the tau weight, that 0.18. And then we're going to run the epoch. So we're going to call the epoch command. Now this run epoch is a really, really long bit of code. And we're going to skip the first 420 lines. That's where Yuma consensus happens. That's probably going to be another great video, another one of these long epic videos. But we're just going to skip it at this point because it doesn't really help us so much. But what happens here is we set all of the Yuma consensus, goes through and looks at all the weights and everything, and then this figures out the emission for both the miners and the validators. And so we get down here to line 869, and we're going to pull that out for every single hotkey. Let's go through, get the hotkey, get the miner emission and the validator emission. So we're just going to extract that from everything that just happened in Yuma consensus. and store it in hotkeys. So if you remember, here are validators. They have dividends, and miners have incentive. So that's why they're stored in two different locations in this new hotkeys variable that we created. So again, here's the incentive and here's the dividends. So now the next step is, as you remember, this is all of the pending alpha. This is what got sold to root, but it should be 4141 miners to validators. And so now we're going to find that other bit of validator alpha that's going to go to the alpha share of the stakeholders. And so we're going to do that math now. The first thing we do is we get the incentive, so the miners bit. And what's interesting is if there are no incentives, then all 82% here goes to the validators. So if this incentive sum is 0, then it all goes to the validators. But if it's not 0, if the sum of the incentive is not 0, then the pending alpha is going to be the pending swapped plus the pending alpha, right? Pending alpha plus pending swapped. We're back up to 82%. Then we divide it by 2, we're at 41%. And then we subtract out that pending swapped, and that's our remaining validator alpha. So we did a little bit of math here to get to 82%, divide by 2, and then get rid of the bit that we already sold off to tau. And then that is our pending validator alpha. Otherwise, it's everything that's left over. Okay, so now we're on our journey to distribute all of the alpha. We've now taken that alpha stake and found the alpha to the stakeholders and then to the miners, and this adds up to 41%. So the main divisions have been made between root validators, alpha validators, and miners. So now we have to calculate how we're going to distribute the dividends and the incentive. That calls this calculate dividend and incentive function. And that calls the calculate dividends and incentives. So first we need to figure out what they are before we can distribute them. So what we do is we grab that hotkey emission that has the hotkey, the incentive, and the dividends. And so then we grab the incentives and the dividends from that. So we grab for all of the hotkeys, incentive, and dividends in the emission, we grab all the incentives. So this is the incentive going to the miners, and we just grab all of those incentives for each one of the hotkeys. Distributing the alpha to the miners is simple, but distributing it to the validators is a little bit more complicated, because if you recall, when we're dealing with validators, we're dealing with child validators and then parent hotkeys that stake their tau to the child hotkeys. And so what we need to do is we need to get the dividend distribution for all the parents and all the children. So it's a little bit more complicated. We've got a lot of math to go through here. And so what ends up happening is we're starting over. We're going to start again with that 41%, and we're going to figure out the allocations between the child and the parents and get that allocation straightened out. And then once we have that allocation straight out, we can go back and divide it back to root and to alpha and continue through the distribution of the alpha. So as you remember, we have a child hotkey, and then this is the family stake. This is all of the stake added up for the child and all the parents. And this is the dividends that is going to all of the parents and children. So we call it the family dividends. And so here is the child with their stake, and then the parents, and I cut it off because there were a lot of them, but you can see how this works. We're going to get the dividends for the family and call that the validating emission. And then the way the data is stored on the chain is we have the data, the proportions for all of the parents, but not for the child. And so what we do is we start with the remaining emission at 100%. And as we go through each parent, we're going to subtract out their emission, and whatever's left over goes to the child. The other thing that we're going to worry about here is the child key take. And so just as a reminder, the child is running the infrastructure, and they can have a take from all of the validators. So when we figure out how much goes to the validator, then the child key takes a small percentage of that. So we start off, we get the child key owner, and we figure out we have some variables, how much is going to the parents, and the total take going to the children, to the child, and it starts off at 0. We get the total contribution, how much total is being given out, and then we create a vector of contributions for each hotkey, for each parent, their hotkey and the amount. So if you remember, the tau weight is 0.18 and it's defined on chain. The next step is to find the contribution of the child. What's the dividends distribution for the child? And we're going to get that through the self-contribution function. Parent and child hotkeys don't need to use 100% of their alpha and root on their child. They can actually create parent hotkeys on other children. So you can see here in this example, tau stats has 30% to this hotkey, 30 to this one, and 40 to this one on subnet 75. So it's possible that the child hotkey isn't giving 100% of their emissions to their own child hotkey. And so we need to calculate that. What happens is we grab all of the child hotkeys for that hotkey. The remaining proportion is 1, and we subtract off all the other children. And when we subtract off all the other children, we're left with the percentage for that child hotkey. Once we have that percentage, we can get the tau weight, the amount of total stake they have on root, the amount of total alpha that they have, and we can calculate their contributions. We know the percentage times the amount of alpha. That's how much alpha they contribute. We know how much tau they have staked on root. We know the tau weight at 0.18. We know their proportion, and that's their root contribution. The combined contribution is then the sum of alpha and root. And what we end up with is the alpha proportion, the root proportion, and the stake weight. The combined is that stake weight. We then add that total contribution. We add that self-contribution to the total contribution. Start off at 0. We've now added in the weight, the stake weight for this child validator. We now want to do the same thing for all of the parents. So we get the proportion and the parent, and we find the proportion. We get the root, the alpha, and then we find their percentage, right? We know the percentage times the alpha contribution, root, the root weight, their proportion, and that's how much goes to root for the parent. The combined contribution, again, this is the stake weight, it's alpha plus root. So now we've calculated that for with the self-contribution for the child, and we've done the alpha proportion, the root proportion, and the stake weight for all of the parents. We add the parent's contribution to the total contribution, and then we store it in a array for later use. And now that we have all of the parent contributions, and we know the dividends, the emissions that are being distributed to all of these validators, we can get the emission factor. The emission factor is their contribution divided by all of the contributions, right? It's a percentage. What's this percentage of stake that this validator, this parent has on this child hotkey? And then we can multiply that percentage times the amount of emission, and that gives us the amount of alpha going to this parent. We can't calculate it directly for the child, so what we do is we start off with the total amount of emission and subtract off all of the parents. For each one of the parents' emission, we need to find out what the take is. What's the child take? And there's 2 ways to calculate the child take. If the parent is from the same cold key, it's 0. So in this case, the child is Yuma and the parent is Yuma. There is 0 take here. But otherwise, you get the child key take proportion and you multiply it times the parent's emission. And that's how much this parent will pay to the child hotkey take. So for each parent's emission, we need to update that. The parent emission minus the amount of take becomes the new parent emission. And we start summing up the child hotkey take here by just adding in that for each one of the parents. So now we figured out this, the dividends for the child, the dividends for the parents. We figured out the takes. And so what we do is we can take the dividend tuples, the dividends for all the parents, and store them. And then for the child, we have the remaining emission, whatever was left over from the parents. And then we add in the take that was taken from all the parents, and that becomes the child emission. And we also save that in the dividend tuples. So now we've gone through and we found the parent-child distribution. We've accumulated the dividends for every single hotkey. And now we have the incentive and the dividends for the miners and for the validators. So we did all of the work here. We had the total alpha. We split it up between the parents and the child. For each one of the parents, we found the child hotkey take and distributed that. And so we can simplify this to the parent-child hotkey allocations, and we now know the correct emission for all of the validators. And we also know the emission for all of the miners. Our next step is for all of the validators to find that root alpha split. How do we divide up their dividends to root and to alpha, and then distribute that to all of the stakeholders? So the first thing we're going to do that is get the stake map. How much stake is in root and how much stake is in alpha for all of the validators. So here's the get stake map function for all of the hotkeys that are validators. We're going to get the alpha stake and we're going to get the root stake and insert that into this stake map. So we have that for all of the validators. As we calculate the dividend distribution, we have the pending validator alpha. We have the pending tau. The tau weight is at 0.18, which we will use to factor the amount of root stake that they have. We have the stake map that we just calculated, and we know the dividends. And so with all of that, we can come together and figure out how much tau and how much alpha goes to each one of the validators. And we'll eventually come to this ending of the emission distribution. So let's calculate that dividend distribution. We take in all those inputs that we just discussed. We'll set 0 to be 0. We want to add up how much goes to root, how much goes to alpha. So we set these totals to 0. We know our root dividends for each one of the validators. We're going to calculate the alpha dividends for all of our validators, and those will go into these vectors. So for every hotkey and every dividend in dividends, the first thing we need to do is figure out the percentage that is going to go to root and the percentage that is going to go to alpha. So we get the alpha stake, we get the root stake, we convert the root stake to alpha by taking the root and multiplying it times that 0.18. The total alpha is alpha stake plus root alpha. Alpha stake plus root alpha, that's the total alpha. And so the percentage of this validator stake that is on root is the root alpha divided by the total alpha. And those numbers are shown here in the metagraph, the percentage of their stake that is on root. So now that we know the percentage that's on root, we can take their dividends and say this percentage of it is going to go to the root divs, and the difference, the dividends minus the root divs, goes to alpha. So we've now broken it apart to root and alpha, and we're going to record the alpha dividends into our vector. And then we're going to sum that into the total alpha divs. So we've got the alpha divs for validator 1, validator 2, and we're going to accumulate these in here. Same thing with root dividends. We're going to calculate all the root dividends and then get the total root divs here. Now, in order to actually give that out as tau, we have the root dividends and the total, so we can get the percentage. And so the root share is the root dividends divided by the total root dividends. That's the percentage of the tau that's going to go to this validator. And so our root tau is this root share, that's percentage, times the amount of tau that we've sold in the last epoch for that subnet. And that's going to tell us exactly how much tau goes to that validator and all of their stakeholders. So now we're going to record that in the tau dividends. And now we're going to do the same thing for alpha. So we find the proportion of alpha dividends. We find the alpha share, which is this validator's alpha divs divided by all of the alpha divs, giving a percentage. We know how much pending alpha there is, so pending alpha times that percentage gives us how much alpha they're going to get. We record that, and then once we're done, we can have the alpha dividends and tau dividends for all of the validators in the subnet. And there we go. We've done all of this, every single block. At the end of the epoch, we finished the rest of it, and we now know how much goes to all of the miners, and then for all of the validators, how much of it is going to be awarded in alpha and how much is going to be awarded in root. And now we know what it all is. We're now ready to distribute those dividends and incentives. We know the net UID, we know the owner cuts, we know the incentives for the miners, we know the alpha dividends for the alpha section of validator, and we know the tau dividends for all of the validators that it's going to go to the root stakeholders. So here we are, we're in the final stretch. We distribute the owner cut. So we know the owner hotkey, and we increase the stake for the owner hotkey. Next, we're ready to distribute the mining incentives. Now, there's a trick with mining incentives. If the owner hotkey is getting mining incentives, that gets burned. So it is, if the hotkey is equal to the owner hotkey, we burn it. We don't award it to anyone. But for everybody else, we're going to increase the stake for that hotkey and cold key on the subnet. So now we've done the owner's cut, we've done the miners, now it's time for the validators. The alpha divs, we have the alpha divs for every subnet. We have to then take the take. So remember, each validator has a take that they are awarded, and then the rest goes to the stakeholder. So we find the hotkey take, we remove that from the alpha divs, so we calculate that because the take times how many is there gives me the take. Then we give that alpha take to the validator. And then for all the other nominators, we then increase the stake for the hotkey on the subnet from what's left over. We do the same thing on root. We have to find the take. The root tau is the root tau minus whatever the take is. We give that take to the validator on root. So the validator actually gets this in tau. And then the rest is given out and distributed to all of the nominators on the subnet. So there we have it. It took us a while, but we made it through what happens every single block in the way that tau and alpha are emitted into the pool, and then the one alpha to the stakeholders. And we broke it apart, delivered in the first every block to the subnet owner, the root alpha, and the alpha stake and miners. And then at the epoch, we calculated the rest of this. Thank you for hanging out with me through this video. If you like in-depth videos like this, let us know because we can create more of them. They're a lot more work, but they're also really fun because we really get into how it really works, which is a very powerful knowledge for us to have as users of the Bittensor network.